Assalamu alaikum. Welcome to another session of Data Structures and Algorithms using C++. My name is Dr. Bilal Wajid, and today we're going to teach you how to find the determinant of a matrix. Now, this is normally a function I ask my students to make. It's a non-trivial problem. In other words, it does require significant thought to go into this. And it requires more thought if you're really making a function that finds the determinant of any n by n matrix, not just 2 by 2 or 3 by 3, which are the easy ones, but any 4 by 4, 5 by 5, or any n by n matrix. So this symbol represents the determinant of a matrix, and this is a scalar value. A determinant is a scalar value which is applicable only for square matrices. So it has to be a 2 by 2 or a 3 by 3 or a 4 by 4 or an n by n matrix. You can't have different number of rows and columns. A determinant is very helpful if you want to find the inverse of a matrix, or the system of linear equations or calculus, and really it's useful in a lot of things. Now, this is a two-dimensional array, and we've discussed this in lecture number 16 as well. So this two-dimensional array is in fact our matrix. Now this matrix can be represented by m, which are the number of rows and columns, because it's a square matrix. Remember, for determinants we need square matrices, and a pointer p. So the pointer p will help point to the first element of the matrix, and then p plus 1 can point to the second, and p plus 2 will point to the third element, and p plus 3 will point to the fourth element, so on and so forth. I mean, if you want to have a revision, I would strongly recommend to go back and look at lecture number 16, where I've done this in a step-by-step fashion. Now, in some sense, we really need just m, which are the number of rows and columns, and a pointer p to refer to any m-dimensional matrix. So hence, with this m and p, we're going to start building our function. So our function is double. It returns an answer of the type double. The name of the function is determinant, and it requires just two arguments. The first is m, which tells us the dimension of the square matrix, and the other one is p, pointer, which points to the first element of the matrix. Answer is of the type double because you can expect the determinant to just really blow up and become a big value, and also the elements of the matrix could be non-integer, but I'm assuming integer for now, and hence the answer could be a big value. We're going to initialize it to 0 because it's going to be a running sum. Now let's consider the simplest matrix, which is a 1 by 1 matrix. So a 1 by 1 is a square matrix. Remember, I keep on highlighting this again and again. The interesting thing about a 1 by 1 matrix, it's actually a singular number, and all singular number in one sense are a 1 by 1 matrix. Now this is interesting, is because that's the foundation of this very powerful software called MATLAB, which is Matrix Laboratory. And the idea they use is that every number is a matrix. Even singular numbers are matrix. So here is 3, which is a single number, and that can be represented as a 1 by 1 matrix. Here's another number. It can be represented as a 1 by 1 matrix. Now the determinant of this single 1 by 1 matrix is the number itself. And that's interesting. That's why you should notice the similarity between the more absolute symbol and the determinant symbol. They really look the same, right? It's just this vertical bar on both sides of the matrix itself. So a 1 by 1 matrix, if you want to program this, you'd write it down as that if m is equal to 1, answer is whatever the contents p is pointing to. So for a 1 by 1 matrix, if the element is 1, the answer is also 1, right? Now it's interesting to note here is because you always start with the stopping criteria. In the last lecture we talked about recursive functions. Whenever you start building recursive functions, you always start with the stopping criteria. So the stopping criteria is 1 by 1 because that's the simplest matrix, and then 2 by 2, which is the other simplest matrix. So for a 2 by 2 matrix, this is what a 2 by 2 matrix looks like. The determinant of a 2 by 2 matrix is AD minus BC, right? And if you want to program this, it's simple, because you're going to say, well, if M is equal to 2, that means it's a 2 by 2 matrix, right? You already had P, which is the pointer pointing to the first element. So the first element A is the contents of location P, B is the contents of location P plus 1, C is the contents of location P plus 2, and D are the contents of location P plus 3. And the answer for that is AD minus BC. So you really need 4 variables, additional variables. And you will see as we proceed that the number of variables required in this particular function will just grow exponentially. So the two together, the 1 by 1 and 2 by 2, are the simplest matrices, square matrices that we have, and they together in fact form the stopping criteria of our recursive function. So joining them together is, again, I'm putting this in if block because whenever you start writing recursive functions, you start with the stopping criteria and then you have the else. So you program the if first, which is the stopping criteria, and then what happens, well, if it's not the stopping criteria. Okay, so putting then this together, you have if M is equal to 1 or M is equal to 2. So if M is equal to 1, you just give the value itself. So answer is whatever the contents of location P are, which is 5.3 in this example. Otherwise, it's M equal to 2, in which case you need 4 additional variables and you need to store them A, B, C, D, and you have the answer. Okay, so now we go to the non-trivial part, and this particular function that I'm discussing here really can handle an n by n determinant matrix. La hawla wa la quwwata illa billahi al-azim. This takes a considerable time of thinking. So what happens, how do you program something that can handle a 3 by 3 matrix or a 4 by 4 matrix or even an n by n matrix, right? Really, this was a hard, la hawla wa la quwwata, this was a hard illa billahi al-azim problem. And I usually give it to students because a lot of them usually start thinking that this is going to be a simple course and it's going to be, you know, a walk in the park. It's not really that way. And that's why even these tutorials that I'm making, normally this particular video took me about 3 complete days to make this video. So the answer really lies in using a recursive solution, and we've already talked in the previous lecture how to build recursive solutions. And recursive solutions start with the stopping criteria, and we have already discussed the stopping criteria, which is a 1 by 1 and a 2 by 2 case. So the only thing left is, how do you proceed ahead? Well, consider the 3 by 3 matrix here. So now we're going to consider the else block, and now we'll learn, you know, how to program the else block. We've already discussed the if block. So this is a determinant of a 3 by 3 matrix. Notice you take the first element A, and then you remove the rows and the columns corresponding to A. So you're only left with this smaller determinant, a smaller matrix. So this is our outer matrix, this is our inner matrix. So you're left with E, F, H, I, and you have to find the determinant of that, right? So in other words, the bigger determinant is calling out these smaller determinants. So that directly is an indication of a that we need a recursive solution, right? So the next is guy B. So B, you discard the row and the column corresponding to B. You're left with D, F, H, G, and I, and we see that here. And the last we're going to consider C. So you remove the row and column of C. So you're left with this inner matrix, which is D, E, G, and H, and we have that, and we have to find the determinant of that. Now you notice one additional thing here are the sign. The sign is positive here, it's negative here, and it's positive here, so the sign flickers. Consider a 4 by 4 matrix now. A 4 by 4 matrix, again, you're always considering the first row here. So you're going to start with A and then B and then C and then D. For example, let's consider C. So for C, you're going to discard the row and column corresponding to C. You're left with E, F, H, right? E, F, H, I, J, L, M, N, and P, right? So this bigger determinant, remember these solid bars, vertical bars represents the determinant of this matrix. So this bigger determinant or the outer determinant is calling an inner determinant with a smaller matrix. So they, again, there's right there an indication we need a recursive solution. So again, notice here the sign flickers. So it was positive, negative, positive, negative. So we need a variable sign to multiply with our inner solution. And how do we do that? Well, it's easier, right? This is our else block. We're going to have a new variable sign. It's going to have this positive 1. And in every iteration, we're just going to flicker the sign. So if it's positive 1, in the next iteration, it's going to be minus 1. In the next iteration, it's going to be minus 1 times minus 1, which is plus 1. And the next iteration is again going to be minus 1. Now students sometimes use power functions, so they would say power minus 1 comma I. So I, when it's 1, I mean you can use that as well. So it's square and then cube and then 4, but I like to use it this way. It keeps it simple. The other important thing here, once you've done with the sign, is let's go back and see this again. You actually need the first row. We're always in this particular formulation, we are always going to consider the first row. So you need a format, you need a framework whereby which you can find A and then B and then C. We've already considered the sign. Now even in case of a 4x4 matrix, you need to have a way out to get these A, B, C and D, right? These first elements. Now you can do that by using an inner loop, right? This is where our sign gets flickered, right? So it's get initialized to +1 in the else block, and then it gets flickered every time the loop executes. Now for getting our first elements A, B, C, D, we need 2 additional variables. One is I and other is basic. Remember I said, the number of variables for this particular function gets blown away. So again, you have this loop, I starts from 0 and goes all the way till m minus 1. And the basic is the point location pointing to p plus I. We already have p and m from the arguments of the determinant function. So initially, basic is A, which is location p plus 0. And then basic has been assigned location p plus 1. Which is B, and then basic in the third loop becomes C because that's P plus 2, and then P plus 3, and so on and so forth. So the basic variable actually holds this element, right? A, B, C, and D. So now we have the sign, we have these basic elements A, B, C, and D, and now comes our inner determinant. And together these 3 things multiply together, we become sign times B times the inner determinant. So now we have to figure out a way how to find this inner determinant, and that's really the non-trivial part. And you can program this. Here is the program again, is that I'm referring to this as the inner solution, where we are multiplying the sign times basic times the determinant, and that's where the recursive call takes place, because you're passing in a smaller matrix. So if it was a 3x3 matrix, you're passing in 2x2 matrices, so the size of the dimension gets reduced by 1, and then you're passing a new matrix Q, right? You're not passing this matrix, you're passing different matrices. So you have to figure out a way how to initialize this new matrix Q. And obviously before initializing it, right, you have to declare it. So integer pointer q, and pointer q has been initialized to have this memory allocation of m minus 1 times m minus 1. Notice this new, it's a dynamic memory allocation. It's m minus 1 times m minus 1 because a 3x3 matrix gives you a 2x2 matrix, or a 4x4 matrix gives you a 3x3 matrix, okay? And then this guy here, this loop here is where Q gets initialized. Okay, so let's look at how to initialize these things for a moment here, right? So for a 4 by 4 matrix, let's say you're considering 2, so you remove these rows and columns and you're left with this. In other words, while you're proceeding with the elements one by one, right, you have to put some conditions in there such that whenever this element's row and column comes in, you don't initialize Q. So if you are looking at this element, you don't initialize Q, but when you are here, you should initialize, you should update Q, you should add elements here, and when you're here, you should not, 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 and then you should. In other words, you really need some conditions to ensure that whenever you're in this region or in this region or in this region, you should not be updating Q. And by the process itself, you will end up with a smaller matrix, right? From 4 by 4, you'll end up with a 3 by 3 matrix. Okay, so the outer matrix has dimensions m, has this pointer p, and L helps us traverse through the elements one by one. And the inner matrix has dimensions m minus 1, has a new pointer q, and has then a variable n, which helps us traverse through the elements one by one. So for the outer matrix, you need m number of rows, p pointer, L variable, and one loop to access the basic elements of the first row. And we've already discussed that, right? So basic elements of the first row, which was A, B, C, D, you can do that by this. But for our proceeding ahead, for our inner matrix, you have m minus 1 number of rows, you have a new variable pointer q and n to allow for us to traverse through the elements step by step. Now you need 2 loops here, right? So here our L has been initialized to 0 and n has been initialized to 0. We actually need to do this every time. L is needed for the outer loop, outer matrix, and n is needed for the inner matrix. Now we need 2 loops, right? We need 2 loops to access the elements. The outer loop was actually for the basic elements, which was A, B, C, and D. It is the inner loop here which we need, okay, for accessing the individual elements. And again, you see we are having this J and K. So again, now you need I, J, K, L, M is already an was the argument of the function, N, and then P, is the pointer, and then Q. So the number of variables in this function is huge. So this is the whole thing that's been written here, okay? So this is our inner loop. This is how we initialize Q. So this is our condition. So notice whenever J is 0, because we in our program are always taking the first row. So whenever J is equal to 0, you discard all the elements in the first row. But the other option is when I is equal to K. In other words, if it's this guy, you discard the second column. And in the third case, you do not include the third column. And if you're considering 2, you by including J equal to 0, you're already discarding this row. And by ensuring I is equal to K, you're discarding this column, right? Because J corresponds to the rows and K corresponds to the columns. So whenever it's corresponding to the same column, you disregard this and you're left with the inner matrix here, right? So basic, let's say if you're considering 2, basic will hold the value 2, and then J and K will again traverse through all the elements, right? Where J corresponds to rows and K corresponds to columns. And if we are considering 2, we only want to have these elements in our matrix Q. So whenever J is equal to 0, that means discard all this, the 0th row. And when I is equal to K means whenever K is in the same column, just discard this, you're only left with this. Here I'm only incrementing n whenever I'm initializing k, right? Whenever I'm adding an element in Q, this smaller matrix, then is the only time I'm incrementing n. And whenever we are done incrementing one matrix, you again just initialize this to 0, and then the whole process starts again. Lastly, once you have Q initialized, you're going to call out this function determinant, hence the recursive call, with a smaller sized array, two-dimensional array. So for 3 by 3 or for a 4 by 4, you'll end up with a 3 by 3, and you're going to pass in this smaller matrix Q. It's going to give you the determinant, and then this is our inner solution, right? Sign times basic times determinant, and the answer in fact holds the determinant. This entire here is the kernel of the function. In other words, this is the difficult component, right? And you can try running this in the terminal. So here I have the whole function itself, right? Here is the main function. Within the main function, I'm just asking it the number of rows. I'm declaring a pointer with that many number of elements, and then I'm initializing the array. I print the array, and then I call out the determinant. The initializing array has already been discussed in lecture number 16, so if you wanted to see how that works, you can go back. The printing the array, two-dimensional array, so this can print any, actually not just a two-dimensional, it can print any two variable size two-dimensional array, and this has been discussed in lecture number 14, and you can go back and see. And this is our function of determinant. Okay, this is our stopping criteria, where m is 1 or 2, it's a 1 by 1 array, or it's a 2 by 2 array. That's our stopping criteria. And this is our else block, right? This is where all the magic happens, right? I'm putting a lot of cout statements. They actually helped me. I would recommend you as well to put a lot of cout statements, especially when it gives you problems in figuring out where did the logical error take place. The cout statements kind of like help you finding that out. And because I'm initializing a pointer here, I always delete it, right? Hopefully in the next lecture I'm going to talk about dangling pointers and why is it absolutely necessary to delete these pointers. Even in the function, main function here, whenever I'm initializing p, I always delete it prior to returning from the function. So here is this, here are my list of programs. So I'm going to compile this. So G++, this is, I've stored this in lecture 20. So G++ lecture 20 CPP -O lecture 20. You can always press the tab button and it will fill up the whole thing. Press enter. It actually does, it works. So now running it, you can see a new, this is the executable which just suddenly popped out. Let's run this for a simple, so it's asked for the number of rows. Let's say it's just a 1 by 1 matrix. Let's give it the value 6. And it says, well, the determinant is 6, but that was easy. It was a 1 by 1. Let's try running this for a 2 by 2. So let's say the answer is, let's initialize the matrix to 5, 4, 3, and 2. So this is our matrix 5, 4, 3, and 2. So the determinant is 5 times 2, 10, minus 12. The determinant is 10 minus 12, so it's minus 2. The answer is correct. Let's try running this again, this time for a 3 by 3. So let's just do this 4, 3, 2, and then 2, 3, 1. It could be any number really, 2, 1, 3. So this is our this is interesting. This is our matrix 4, 3, 2, right? In the first case, it takes out the number 4 and then the smaller matrix 3, 1, and 1, 3, and the sign is positive. The basic is 4 and the determinant of this is 9 minus 1, 8. So 4 times 8 becomes 32. In the next instance, it takes the number 3. We see that here. and the matrix 2 1 2 3, we see that here 2 1 2 3, and the sign is -1, right? The sign flickers. The basic guy is 3, and the determinant is 6 minus 2, which is 4. 3 minus 4 is 12. In the last instance, we take this element 2, right? And 2 3 2 1, we see that here, and again the sign is 1, basic is 2, and the determinant is 4. The answer is 12, right? So that was again easy. Let's try doing this for a 4 by 4. So I'm going to clear this completely. Let's run this for a 4 by 4, and I'm going to start doing this quickly because, you know, I'm just putting the values here. So this is our 4 by 4 matrix. So that's our 4 by 4. Let's, rather than going through this, because I've already checked this, so it works, rather than going through this step by step, I mean, let's just see what's going on. So I expect a 4 element coming out here, and this smaller 3 by 3 matrix 2 1 2 3 2 1 3 2 1, and we see that here. And this 1 3 by 3 matrix is going to call out 3 2 by 2 matrices. So you have 2 here. It's going to call out 2 1 2 1, and then 1 here. It's going to call out 3 1 3 1, and then 2 here. It's going to call out 3 2 3 2. That's here. And once that's all done, it's going to give us the determinant. And then after 4, it's going to pick up 5. We see that it picks up 5. It picks up 1 5 4 1 2 2 2 1 1. That's our 3-dimensional matrix, right? And then it repeats the process, right? If it's 1, it's going to be 2 1 2 1. I mean, in other words, for every value here, it gets a 3 by 3 matrix. Every 3 by 3 matrix opens up 3 2 by 2 matrices, and we have the answer. And then the next element picks up. It picks up a 3 by 3 matrix. Every 3 by 3 matrix picks up 3 2 by 2 matrices, and the process again repeats again. In other words, for a single 4 by 4 matrix, I should expect 4 3 by 3 matrices. So that's one, that's the second one, that's the third one, and that's the fourth one. And every 3 by 3 matrix should give me 3 2 by 2 matrices, and we see that happening here. The final answer is determinant -1. Okay, so this was a very difficult question. Interestingly, there's not a lot of solutions out there online that you can find. I am publishing this in July 15, 2020, and I didn't see a lot of online solutions for this anyhow. So hope this helped. If you like this video, press like. You know, I want you to press like on this one because it took me about 2-3 days to make this video. And subscribe and hit the bell icon for new videos. Thank you very much. Up until next time. Bye-bye.